Section 3.2 measures of variation for statistics, and we are now talking about the empirical or normal rule. Empirical rule is what you usually hear it called. We talked about Chebyshev's theorem. Let's revisit real quick, where you can determine the approximate proportion of values that falls within a certain distance of this mean. Well, here, the empirical rule is an understood rule that does the same thing, but very specifically for a normal or bell-shaped distribution. So, and you guys are going to get used to this a little bit later on, but we're going to do it now. You may remember it from Algebra 2. If your mean is here in the middle, let's make it x bar because that's what they used in the book, and I don't want to confuse you. So let's do x bar. Then I come out usually 1, 2, 3, 1, 2, 3. So this would be x bar plus 1 standard deviation, x bar plus 2 standard deviations, x bar plus 3 standard deviations. And the other side you subtract 1 standard deviation, subtract 2 standard deviations, and subtract 3 standard deviations. So in a normal distribution, what usually happens here is your data falls under a really pretty bell-shaped curve. We'll learn more about that soon. But what we know from the empirical or normal rule is that 68% of my data falls within 1 standard deviation. Oh, wrong one, Miss. Try again. I didn't do that curve very well. They're supposed to be about equal. So I don't know why I'm going crazy with my lines here. This is approximately 68% of my data, okay? And depending on where you got your numbers, it might say 68.2%, but 68% is what we usually go with. And then within 2 standard deviations, which would be here, is 95% of my data. And within 3 standard deviations, which would be here, is 99.7% of my data, which truthfully leaves a negligible amount of data outside of that. So there's not very much at all. So what they're looking at here and what they're usually going to have is 68% of the data falls within 1 standard deviation of the mean. This is within 2 and within 3. So using the word within means it goes in either direction. So from -1 standard deviation to +1 standard deviation. That's what the empirical rule looks like, and we'll use that more later on. We want to talk real quick too about linear transformations of data. So suppose you own a small store with 5 employees. Their hourly salaries are $10, $13, $10, $11, and $16. And it says find the mean of these salaries. So if we add these salaries up and divide by 5, we have x bar equals $12. The standard deviation of the salaries, if you put them in your calculator or used your formula, is 2.550. Okay? Suppose you give each employee a raise of $1 per hour. The new salaries would be $11, $14, $11, $12, $17. What's the new mean and standard deviation? Well, the mean, x bar, is $13 this time. The standard deviation, however, is 2.550. Because adding 1 didn't change my standard deviation. It did change my mean because all of my numbers moved up 1. They're still spread out the same. It didn't change how they're spread out. So suppose that the 5 employees work the number of hours per week shown below. Find the mean and standard deviation of the hours worked. The mean of the hours worked would be 15, and the standard deviation would be 4.123. For 1 month, you double the number of hours each employee works, so you multiply by 2. The new hours, 30, 24, 36, 40, 20. Mean and standard deviation. So let's see here. The mean now is 30, and the standard deviation is 8.246. So hopefully you noticed something here. By the way, this was +1. Right? When each data value is multiplied by a constant, if it's multiplied by a constant, the mean is equal to the constant times the mean of the original set, and the standard deviation is also equal to the absolute value of the constant times the standard deviation. So here, x bar times c, and then standard deviation times c absolute value. Okay, but when a constant is added to the data, instead of being multiplied, you get your x bar plus your constant, but your standard deviation does not change. It's still spread out the same. All right, that's it for section 3.2.